Dear colleagues, friends, distinguished guests, ladies and gentlemen, good morning, good afternoon, and good evening. My name is Shelly Fan, and I'm your MC for today. It is with my great pleasure and on behalf of City University of Hong Kong to welcome you to First International Conference on Heterostructured Materials, HSM1. As part of CTU, HSM1 will bring together all the leading experts from all over the world to exchange views on the recent trends in a variety of topics concerning the heterostructured materials. Now, I would like to introduce all the on-site professors. Let's welcome. Professor David Srolowitz. Professor Jacob Huang. Professor Yuntian Zhu. Professor Yang Ren. Professor Zhaoxuan Wu. Professor Xusheng Yang. Thank you. Without further ado, I'm honored to show you a welcome speech from our President Wei Kuo.
Dear colleagues and academic friends from around the world, welcome to First International Conference on Heterostructured Materials. Heterostructured materials represent an emerging class of materials that are expected to become major research for the materials, mechanics, physics, and computer simulation communities in the coming years. On this incredibly special occasion, over 70 prominent scholars and pioneers in this material field across the globe will get together, albeit virtually, to exchange insights on fundamental issues that need to be probed. This event is a multidisciplinary platform for sharing research and establishing future research directions. CTU aspires to become a leading global university, excelling in research and professional education. It is important to disseminate this research result to the academic community, which will benefit diverse researchers and scientists in material science and engineering, mechanical engineering, chemistry, chemical engineering, biomedical engineering, and biology. I hope all the participants of the conference will find the talks and discussions stimulating, inspiring, and have meaningful takeaways after the conference that will encourage more profound research and collaboration into this exciting field. For CTU, it's an honor to host the first of its kind international conference in Hong Kong, which will be held biannually. It allows us to engage with delegates on great interesting and potential topics. Over the past decade, CTU has been one of the most progressive universities in the world. Our dynamism, energy, and boldness in tackling challenging problems stand out among our many unique features. We aim to make our university a preferred destination, not only for top faculty and researchers who are the driving forces and academic leaders in their fields, but also budding scholars who may not yet have significant record in research, but have great potential. We have revamped and re-energize our university for the future, placing ourselves at the forefront of innovation in a number of important fields. For example, biology, electrical and electronic engineering, computer science and information technology, engineering, and creative media. At the same time, we have identified several niche areas in which we can play a major role in producing graduates and research, including data science, veterinary medicine, energy and environment, among others. The quality of our world-class scholars is recognized globally as well. According to metrics compiled by Stanford University 2021, over 175 CTU faculty members are listed among the top 2% of the world's most highly cited scientists in their respective area of expertise. Compared to faculty size, CTU's percentage of the world top 2% most highly cited scientists is among the best in Asia. CTU is also ranked first among local universities for 5 years in a row in the top 100 universities for granted US utility patents by the National Academy of Inventors. We have launched a large-scale flagship innovation and entrepreneurship program in 2021, Hong Kong Tech 300, which is the #1 university-based large-scale entrepreneurship program in Asia. Altogether, 500 million Hong Kong dollars is allocated for aspiring entrepreneurs among CTU students, alumni, research staff, and others to launch startups and ignite their enterprising journey. We target at creating 300 startups in 3 years. I hope you all will enjoy the conference. Thank you.
Thanks for the President's exciting speech. Now I would like to introduce Professor Yuntian Zhu from our local organizing committee. Professor Zhu will talk more about heterostructured materials area. Professor Zhu, please.
Dear colleagues and friends, I'm very honored and delighted to deliver this speech on this special occasion. First, I'd like to thank the President for his remarkable video address. I'd also like to thank the Hong Kong Institute for Advanced Studies for sponsoring the first international conference on heterostructured materials. As the name suggested that there will be future conferences on this topic also. The second international conference on heterostructured materials will be held in Chongqing in 2024. Chongqing is a city in southern China. The third one is likely to be in a different country like Japan or Korea, South Korea. It is expected that heterostructured materials will become and remain a major hard research field for the next 10 to 20 years because of two reasons. The first reason is there's a new materials science to be studied for years to come. The second reason is their great commercial potential. In fact, the industrial scaling up is already underway. For example, the Iron Steel Group Corporated is already doing this industrial scaling up. And this will be reported later in this morning. This conference series provide a platform for researchers to exchange ideas and to find collaborations. I'd like to express my sincere thanks to everyone who is participating in this conference. I'm sorry that due to the COVID pandemic, most speakers cannot come to this conference on site. But I still hope that you will find this conference enjoyable and exciting. Thank you.
Thank you, Professor Zhu. To commemorate this spectacular moment, may I invite all the professors to come here to take a photo. Please come down. Thank you all. Please take a seat. Please take a seat. Thank you all. Thank you so much for joining the opening ceremony. To kickstart the conference, I would like to introduce Professor Yuntian Zhu, the chair for session 1. Let's pass the floor to him.
Our first lecture will be by Professor Huajian Gao from Nanyang Technology University, Singapore. His title of the talk is Engineering Metals with Internal Interfaces for Enhanced Mechanical Properties.
Can you hear me, Yuntian? Can you hear me, Yuntian? I'm not able to share my slides yet. So you have to allow someone to allow me to share. Oh, okay. Okay, great. Okay. Okay. You can see my slides, right? Okay, thank you very much for, okay. It's my great pleasure to attend the first international conference on heterostructured material. I'd like to thank the organizers, especially Professor Yuntian Zhu, for inviting me. It's my great honor to give the plenary talk here. And also, I wish I could be there in person with you. So let's hope to get together when the pandemic is over. So today I'm going to share you some work done by my former postdoc, Professor Haofei Zhou, who's now in Zhejiang University, my former student and current postdoc, Dr. Ji Li, who's now working at IHBC. And our collaborators are Professor Lei Lu from Institute of Metal Research in Shenyang. And Lei and I have been collaborating for the last decades. And my relatively recent collaborator, Professor Matteo Setta from NTU. Unfortunately, Professor Setta is moving to Cambridge University very soon. Okay, so the background of my talk is the application metals. You know, as we all know, that metals still find wide applications in construction energy, medical devices, space technology, electronics, transportation. Therefore, it's very important to continue to study metals and try to improve their mechanical properties. The active research area for metals, including biocompatible metals, heat-resistant metal, hydrogen-tolerant metal, for example. Lots of mechanical property, including plasticity and fracture behavior, deformation tuning, void nucleation growth, phase transformation factor versus brittle transition, crack propagation. So lots of research opportunities still in this area. And a prominent topic that kept all of us quite busy is a so-called strength ductility trade-off of metals. Right? For example, if I plot normalized strength as vertical axis and uniform elongation metals as the horizontal axis, then it's been long known that by reducing grain, refining the grain size, reducing the grain size, you could increase the strength of metals at the expense of reduce your ductility. So uniform elongation is reduced. So this banana-shaped curve is called strength ductility trade-off, where if you have a coarse grain, the material is ductile, it can undergo large elongation, but strength is relatively low. If you want high strength metals, then you introduce a lot of grain boundary, which block dislocation motion, and which at the same time kill the plasticity, do not allow the material to deform as much. So you have high strength but low ductility. And over the last 2 decades, Professor K. Lu from Institute of Metal Research have been introducing this nano twin material. So essentially, through grain boundary engineering, by introducing twin boundary in the material, the twin boundary can block dislocation, but yet still allow dislocation to pass through. So there you can push the frontier and having improved ductility and strength. So you break off this traditional envelope. So here's nano twin, right? So this material are called uniform nano twin. And in the low strength ductility region, you can improve the strength ductility, this curve, by introducing gradient nanograins. This is also from Professor K. Lu's work. So by introducing this gradient, so in the surface, you have a nanograins, so surface treatment, and in the bulk, you have coarse grains. So you could improve the this strength ductility performance by pushing the frontier toward this region. Now, Professor Lei Lu and I, we've been working recently on a gradient nano twin nanograins. This is like a dual gradient. So both the grain size and twin spacing exhibit a gradient, right? From a very small twin size, grain size region to coarse twin size and grain size regions. So this is the high strength regime. You can further push the frontier through the gradient strategy. All right, this is the microstructure. All right, so let me just say maybe a few words about the gradient strategy introduced by Professor K. Lu. So surface plastic deformation techniques. So you can fabricate this gradient nanograin, so gradient nanograin structure, right? Near the surface, you have nanoscale grains, and through a transition region in the core, you have coarse grain regions. Now we can compare the mechanical properties. If you do not have this gradient structure, just a coarse grain material, you have this kind of low strength but large ductility behavior. So just a gradient nanograin foil, right? Just have this nanograin foil, the surface. So without the gradient material, just the nano twin foil, you have a high strength, right? High strength but low ductility. But in the gradient strategy is to combine the advantage of both the surface layer, high strength surface layer, and ductile core. So you have this composite behavior, the exhibit by this red colored curve. You have with the strength increased by more than 100%, but still retaining ductility, right? Not sacrificing ductility. So this is the exhibiting the advantage of the gradient structure here. About 80 years ago, Yujie Wei from the Institute of Mechanics, so also one of my former postdoc, we've been collaborating with the gradient nano twin structure in tube steel. And this gradient nano twin structure was introduced through the mechanical deformation, through pre-torsion. So you have a bar, cylindrical bar here. So the pre-torsion, you can introduce a gradient structure. Near the core, the strain deformation is small, so you retain the original structure. But near the surface, due to the large mechanical deformation, shear deformation, you can just introduce a very fine nano twin structure near the surface, right? R equal to 1. So R is normalized radius. And so you have this gradient nano twin structure from a core to the surface. There, this twin density can be controlled by the pre-torsion, amount of pre-torsion, right? the zero degree means no pre-torsion. This original material have strength, this red behavior. And by introducing pre-torsion, introducing this gradient nanotwin structure, we can see here, we can increase the yield strength of the material continuously without sacrificing ductility, right? So this exhibit this a combination of nanotwin and gradient strategy. My other motivation for my talk today is this non-laminated HSM strategy introduced by Professor Zhu, our organizer here. So Professor Zhu's group have been working on this making laminated heterostructured material through mechanical processing, such as accumulative roll bonding or asymmetric rolling. So here's one example here by making this copper bronze laminate, right? Copper and bronze laminate. So you can see here this by making this laminate structure. So this shows the shaded region here is all the traditional mechanical property of copper and bronze, various copper and bronze. But just make them laminate, right? Make them laminate. So usually you expect a roof mixture behavior, right? Some combination of behavior, which still will in this shaded region. But this laminate allow you to break through the push frontier here into this region. So this fully demonstrate the advantage of the heterostructured material. By introducing interface in the material, you can strengthen the mechanical property of the material. So here, Professor Zhu introduced this interface effective zone, which I will talk a little bit later. So my topic today consists two parts. First part is HSM by gradient nanotwin microstructure. So I will talk about our collaborator work with Professor Lei Lu. So gradient nanotwin structure, superior strength and work hardening, and introduce the underlying mechanism. Is bundles of concentrate dislocation, or BCDs we call it. This is like an interesting dislocation structure that allow us to see this extra strengthening, work hardening. My second topic is HSM by additive manufacture laminate structure. Professor Zhu's work was through mechanical process, roll bonding, but working with our collaborator, Professor Matteo Setta's group, we have explored how to make laminate structures through additive manufacturing methods. Through this so-called site-specific recrystallization in metals additive manufacturing to achieve enhanced mechanical property. And this is still in the kind of preliminary work stage. So my first topic has been published. This is based on the paper published in Science in 2018 with Professor Lu and a few collaborators. Hao Fei is my former postdoc. All right, so Professor Lei Lu's group are specialized in this fabrication of nanotwin structure, right? So direct current electrodeposition, different temperatures, they were able to fabricate various gradient structure based on 4 components, A, B, C, D. Right? A has very fine twin size and green size on order of like 29 nanometer in twin spacing. Green size about a couple of micrometer, 2.45 micrometer. And D is the most coarsest twin spacing and green size. D is about, with twin spacing about 72 nanometer and green size about 50 micrometer. And BC are the intermediate. So by stacking these 4 basic component material, and Professor Lu's group have successfully fabricated gradient nanotwin structure with various structural gradient. For example, A, B, C, D, one stacking, you have the GNT1, right? Just one kind of this structure, one stacking, such a structure, A, B, C, D. And this is kind of a relatively low gradient. Then we can have a twice stacking, so double stacking. So A, B, C, D, and DCBA, right? This is kind of, in both surface, you have a fine grain structure. And then you can triple it, GNT3, right? We can triple the gradient structure. We can quadruple the gradient structure, GNT4. So this allows us to introduce higher and higher gradient in the structure and explore the mechanical properties. We can validate this gradient structure through hardness measurement. Here you can see that in GNT1, you have a continuous slope of a hardness measurement. In GNT2, right, we double the structural gradient. You can see the gradient here and then rise again, right? And GNT3, we have a triple the gradient. GNT4, we have quadrupled gradient. So here's the mechanical testing of these materials. The four gray curve here are the mechanical property of four components, right? The homogeneous twin structure. NT1, NTA, A is the finest, right? The finest twin. So you can see here, there's a little bit hiding here. So this curve, gray curve here, shows the highest strength, but relatively low ductility. NT2, NTB is the second one. So this circle here, this gray curve, right? The strength is a little bit low, but with increasing ductility. NTC is this triangular circle here with further reduced strength, but larger ductility. And the coarsest one is NTD, this inverse triangle here with a lowest strength, but largest ductility. The gradient structure are the color ones. Gradient structure. GNT1 is with the lowest structural gradient. We achieve the strengths which is exhibiting here, which is shown here, right? The GNT2, we push the strengths higher, right? The GNT3, we have this curve here, and GNT4 we have here, right? These GNT structure, they provide extra strengthening. They are not predicted by the roof mixture. For example, you can see GNT4. It's the combination of four components here, yet their strengths are higher than any of the components. So in other words, the strength of GNT4 exceed even the strongest component, which is the NTA, right? The strongest components. GNT4 is even beyond that. This shows the gradient structure actually beat the roof mixture. So here we predicted, we plot the strength versus structural gradient. You can see by increasing structural gradient, you can continuously increase in strength. But also I should point not only the strength, but also ductility, right? Is way better than the NTA. And also work hardening, strain hardening is also increased, right? With the increasing structural gradient, we can see the work hardening rate also continuously increase. So what are the mechanisms? And the experimental, when we started working together, Professor Lei Lu's group already found this so-called bundles of concentrate dislocations called BCDs. These BCDs, they are dislocation bundles that spans across multiple twin boundaries. So here you can show this under microscope. And these are large super dislocation structures, span multiple twins. They're not confined within a single twin boundary. So the question of interest from modeling point of view is what is the mechanism of the observed extra strengthening, which defies the roof mixture? And what is the origin of BCD? So you can see here that we wanted to explain this amazing behavior that GNT4 is, for example, even stronger than any of the components, right? So here it shows the roof mixture, A, B, C, D, right? These are property. If a roof mixture applies, then you would predict a property along this line, along the interpolation line. But GNT behavior is really above this, right? So this shows extra strengthening, extra work hardening. So my postdoc, Hao Fei, former postdoc, he's faculty now, performed MD simulation first to verify the extra strengthening effects. In the experiment, we have a 4-component A, B, C, D. In the simulation, due to the limitation of the computing power, we have a AB. So we only have 2 components, AB, right? So we have we introduce a structural gradient by having AB or ABAB, right? ABAB have a higher structural gradient than AB, right? So you can see here the mechanical, measured stress strain behavior. The NTA is shown by these, the blue curve here, right? You can see here the blue curve here. NTB is shown by this greenish curve here, right? The gradient AB is given by this curve here, right? And ABAB increasing structural gradients by this, right? First of all, you can see here on this region we call flow region, right? This is where you have lots of dislocating sample in the flow region. The gradient GNT structure beat actually both of the components, right? They completely defy the roof mixture, right, in this region. Here in this region, if you are familiar with MD, we usually do not interpret as much because in the molecular dynamics sample, we start with a very clean sample. So nucleation, we call this nucleation dominant regime. Nuclear dislocation so we do measure this region, right, where you have lots of dislocation of structure. And so here, we see MD simulation verified extra strengthening effects, where the flow stress increasing with the structural gradient as observed in experiments. We also check the statistical equivalent microstructure to make sure this is a statistically sound conclusion. We changed the microstructure of GNT1, randomly changed the green structures, right, by keeping it statistically identical. They have same average green size, but the actual one is kind of randomly shuffled. We see the same flow stress. So they're not sensitive. So they're not a result of a structural statistical fluctuation of our simulation. Now, what is the format? Now with the computational tools, we can investigate further the mechanisms. So the formation of BCD in MD. Okay, so let me first introduce this well-known kind of dislocation structure and layer structure here. So in our experiment simulation, we have this kind of parallel twin, right? All the twin boundary all parallel to the specimen surface, sort of parallel to loading axis. We're loading parallel to the layer structure. If you're familiar with the deformation of the layer structures, you know the threading dislocation concept. These dislocations are propagating between the layers, okay, layer structures. If you have a multi-layer structure, these are kind of well-known dislocation structures called threading dislocations. And we call this mode 2 dislocation or hard 2 mode, right? Mode 2 dislocation. We call it a hole patch type dislocation, like dislocation pile up against twin boundary. We call them mode 1 dislocations. In the nanotwin structure, there's another mode called twinning partials. These are if you have a large shear stress, resolved shear stress on the twin boundaries, you can initiate the Shockley partials, the twinning partials. We call it soft mode, okay, mode 3 or soft mode. So in this gradient nanotwin structure, we observe in the initial stage of deformation, there are regions we observe mode 1. Okay, so in a homogeneous, without gradient structure, in a homogeneous nanotwin structure, if you load parallel to the twin boundary, we only observe mode 2 dislocation, which is threading dislocations. Okay, because there's a gradient, we observe some regions appear to be the mode 1, nucleation mode 1 dislocation, while the other regions still mode 2. Then the interaction between mode 2 and mode 1 dislocation induce the concentrate dislocation, induce the concentration of dislocation near this region where mode 1 dislocation are nucleated. So saying that the formation of BCDs are intimately connected to the interaction between mode 1 and mode 2 dislocations. Here's a more like three-dimensional view. In the concentrate dislocation region, we have this nucleation of mode 1 dislocation from the interface. This is the loading axis, right? These are the mode 1 kind of hole patch dislocations. In the other regions, we have a mode 2 dislocation. They are threading dislocations probably between the twin layers. Now our experimental colleagues then turn to their samples. By changing diffraction vectors, they were able to observe dislocation of different Burgers vectors. So they were able to indeed confirm near the BCDs, there are lots of mode 1 dislocations. Okay, in the other region, there are lots of mode 2 dislocations. These orange are mode 2 dislocations with mode 2 Burgers vector. Near the BCDs, these are lots of Burgers vector in mode 1 type Burgers vector. Now, by further looking at the dislocating composition in BCD and surroundings in the MD simulation, for example, we compare the window 1 and 2. Window 1 mostly focus on a region where with BCDs, bundles of consonant dislocation. The region 2 are kind of outside the bundle in the surroundings. We can see that in the window 1, the dislocating density is much higher. There are 10 to the 17, right? In region 2, the density is 1 order magnitude smaller, 10 to the 16. In the region 2, window 2, they mostly consider Shockley partials and some steroids, but not too many, 3% steroids. In the region 1, where BCDs are sitting, we find 85% of Shockley partials, but with a substantially higher composition of steroid dislocation. These are sessile dislocations. And so it seems to us that formation of steroid dislocation are the key to form these BCD bundles. So how do they form? So we look at the partials associated with mode 1, mode 2. We see these partial can react. Okay, delta B and B gamma, right? For example, gamma D, gamma A, gamma B are the partials of mode 1 dislocation. Okay, and delta B is a partial mode 2 dislocation. But these can react. Delta B and B gamma can react into a low energy steroids. And delta B and A gamma can react into high energy steroids. And delta B and gamma D can react another type of high energy steroids. So the partials of mode 1 dislocation, mode 2 dislocation react in form of steroids, which are sessile dislocation. They kind of serve as obstacles to further dislocation motion, and they induce extra strengthening in a GNT structure. So we can summarize from an MD simulation investigation of BCD formation mechanism. First, we have a sufficiently high structural gradient, right? When you introduce this structural gradient, then you have the high multi-axial local stress interface. Because at the interface, you have triple junctions, green boundary and twin boundaries. So you have this multi-axial local stress interface. So this multi-axial stress state help activating mode 1, mode 2 dislocations. Without this interface, you only activate mode 2, but this interface allows you to activate also mode 1. And the reaction between mode 1 and mode 2 dislocation leads to formation of steroid dislocation, which act as obstacle to dislocating motion. And this, because they're obstacle, they induce traffic jam, essentially, right? You have this propagating mode 2 dislocation, but they encounter traffic jam. It's like car accidents. And you form a jam, you build on this traffic jam, you form BCDs. And that induces extra strengthening. More recently, Lei Lu and Professor Tin Zhu from Georgia Tech, we also look at the backstress strengthening in GNT copper. So here, by measuring the backstress evolution, we can see the backstress increasing with structural gradient, while effective stress more or less remain saturated with structural gradient, but backstress is quite sensitive to structural gradient. Okay, so our interpretation is the gradient induce a long-range GND, long-range geometric necessary dislocation, where in a homogeneous nanotwin, the GNDs are more localized. So through modeling performed by Tin Zhu's group, we can see that the stress strain curve, the total tensile stress is represented by this curve. The HNT induced backstress means homogeneous nanotwin structure induced backstress. These are dislocating confined within twin layers, account for majority of the backstress. Effective stress is given here, and the gradient induced backstress provide extra strengthening to the gradient in this. All right, so my second topic is HSM by additive manufacture laminate structure. And this work is still under preparation here. It's led by my colleague, Professor Matteo Setta's group. So again, I'm going to show you this page as motivation. This page summarizes the work by Professor Yuntian Zhu's group through laminate HSM through mechanical processing, through active roll bonding, right? Through asymmetrical rolling, and through this mechanical processing, you form a laminate structure. You can overcome the strength ductility trade-off by introducing interfaces. Specifically, Professor Zhu's group used the interface effective zone to explain this as a way to introduce extra GND in the structures, therefore strengthening structures. So motivated by this, and also in recent years, there's a lot of interest in additive manufactured alloys. through laser melting, through powder bed. One example is work by Professor Morris Wang and Tin Zhu's group. They used an additive manufacture. They were able to make this hierarchical microstructure with length scale spanning nearly 6 orders of magnitude. Right? You can see here again this plotting the strength ductility chart. Right? They were able to make this additive manufactured materials that outperform most existing material. It shows the potential of AM, additive manufacturing techniques, in improving the properties. So we want to combine both. Our question is, we know that through HSM strategy, right, the laminate strategy, we can improve mechanical properties. We know the additive manufacturing strategy allows to improve mechanical property. Can we find a joint, an overlap in place, right? You combine both strategy in improving mechanical property. So we try to explore this. So my colleague, Professor Seta's group, have developed technique using additive manufacturing, the laser melting strategy, to make materials, AM materials, with tunable thermal stability. Right? So here's one example that we call laminated AM additive manufactured 316 stainless steel. So they call this site-specific recrystallization strategy. Right? So for example here, in the as-made material, as-built material, AM material, by having site-specific thermal stability through a heat treatment over 1000 centigrade in a more stable region, right, with a higher thermal stability. So this structure is unchanged, remain unchanged during heat treatment. So we call this non-recrystallized region, where they have finer green structures, more twin boundaries, more low angle green or high angle green boundaries. They're essentially higher strength regions. With lower thermal stability regions, right, we can during the heat treatment, the structure become coarser. They have a green growth through recrystallization. You have larger grains, therefore the mechanical strength is lower. Right? So by controlling thermal stability, site-specific thermal stability through the heat treatment, then you can make this lamellar structures. These are not by mechanical processing, right? It's really just by controlling thermal stability and heat treatment. So you can make coarse lamellar structures or fine lamellar structure, right? Continue this. And here's to show the microstructure there with coarse lamellar structure. We have 5 interfaces shown here. And with the same size, we can fine lamellar structure, we can make 11 interfaces, right? This is just the beginning. So there's techniques still under improvement. And this is preliminary measurement of stress strain behavior. They recrystallized, right? They recrystallized means the green growth and during heat treatment exhibiting a relatively lower strength, larger ductility. Non-recrystallized are thermally more stable region, right? They have a higher strength, lower ductility. But lamellar, right? The fine lamellar and the coarse lamellar regions, there are this red and green curve, right? You can see immediately the laminated steel exhibit extra ultimate strengths. Their ultimate strengths are higher than both of the component material, recrystallized, non-recrystallized. Extra ultimate strengths and also extra work hardening. Kind of similar to gradient structure, right? The ultimate strength is higher than both components, therefore defy the rule of mixture. Although the effects are not as high as in gradient nanostructure, because again, this is just preliminary work, right? We can continue to refine the strategy. And through G&D measurement of geometric necessary dislocation density, we can see the fine lamellar structure, we have a higher G&D density than coarse lamellar structure. Right? The G&Ds accumulated interface laminated AM steels. So I'm going to use adopt the same model or same theory by advocated by Professor Zhu, the interface effective zone. Now we're going to look at this and try to model the system. The interface effective zone is a concept based on the dislocation pileup near the interface. Right? In the soft region, we have dislocation pileup. in the heart region. So the pileup induced backstress due to pileup in the heart region with forward stress. The interface effective zone width is measured by this scale with the shear modular material divided by yield strength square times Berger's factor. This is the length scale, the size scale of the IAZ width. Right? The stress field due to the pileup have this behavior. So essentially the GND pileup induce accumulation of GNDs near the interface or within the IAZ zone. Okay, so to model specifically this additive manufactured material, we develop a constitutive behavior of a recrystallized, non-recrystallized phase. Specifically, we adopt the constitutive model, one of the constitutive model from John Hutchinson, published a couple of decades ago. The strain rate is written in this form. Right? Strain rate is a power law form, but with effective stress, with a scaled flow strength. The yield strength of the material has this two parameter Q and H. Right? The Q and H are to be fitted to experimental results. Now, consider the behavior of the interface within the interface effective zone. We have back stress, so we're going to subtract the effective stress, subtract the back stress from effective stress. Then the flow strengths also have the strain gradient plasticity, right? We have this, so based on previous work on mechanism-based MSG, mechanism-based strain gradient plasticity. So we're eta as the strain gradient. So here's the alpha eta is the strain gradient effect on the yield strengths. And backstress evolution is have this equation here. All right. So based on this theoretical framework, we can start to model this behavior, this laminated, AM laminated material. So you can see we can fit the component material very well. This is recrystallized material experiments, the dashed line, and non-recrystallized experiment dashed line, the dark line here. Our model are these blue colored, right? Are the model. We fit extremely well. Right? Both the stress strain behavior and also work hardening. So we can use this to predict. Okay, so here's the lamellar, our constitutive model also not only capture the recrystallized, non-recrystallized phase very well, but also capture the lamellar structure very well. Okay, the lamellar structure, also the strain gradient. More detail here are shown here. The stress and strain behavior of the coarse lamella. This is a total stress strain behavior we model very well. Right. In our model, we can also calculate the contribution from each phase and interface effective zone. So the contribution from a non-recrystallized phase are shown by this yellow curve. The contribution from recrystallized phase is shown by this pink curve. The contribution from interface effective zone is given here, right? Which is relatively small because our green, the laminated space is still large. In this additive manufactured material, you can see the scale are still quite large. Our interface effective zone, I have estimated, is only 10 micrometer interface, but these laminates are order of magnitude. The thickness of laminates are order of magnitude higher than that, right? So here's fine lamellar, same thing. Right, the contribution from each from non-recrystallized phase, recrystallized phase, interface zone. But you can see the contribution from interface effective zone are higher now, with refined. Right, so we're saying that once we push further, right, we can push further theoretically speaking. For example, we can theoretically there's no limit. Right, we can do computation, 5 interface, 11 interface, 19 interface, 39 interface. We can continually push mechanical property. But unfortunately, current AM techniques, right? Our collaborator, Professor Seta, have tried 19 interface, already see the kind of non-perfect interface. The interface here is more or less intact, but once you have stacked too many interfaces, because the laser scanning, the laser spot have a finite size. So the limited resolution of this AM made material at this point. So with the further improved AM techniques, we hope to push this idea further, right, into higher and higher strengths. But advantage of AM techniques, also not only you can make laminate, you can also make stripe material, you can make staggered material or bio-inspired material with staggered structure. You can make other structures as well. So I think eventually the additive manufacturing technique has a lot of potential to be explored, making different type of HSM, not only laminated, but other configurations. Still question opportunities in the AM, HSM. First of all, atomic scale understanding of the formation process, deformation mechanism of IAZ are still to be explored, to be established. We have a continuous modeling, we have a strain gradient plasticity-based modeling, but the atomic scale understanding of the formation mechanism of IAZ are still to be done. The second one is the improvement, as I say, improvement AM methods for more precision control of interfacial properties, high resolutions. Okay, so I'm almost done. And design novel heterogeneous structure with target properties. Okay, so here's my final page summary. And today I've using two examples to demonstrate potential of heterostructural materials, which is a theme of this workshop. My first topic have to do with showing the simultaneous enhancement strength and work hardening can be achieved through structural gradients in GNT copper. The structural gradient can lead to improved work hardening rate and tensile strength that exceeds even the strongest component of the microstructure. Right? This is not roof mixture. This is way beyond roof mixture. And the extra strengthening work hardening of GNT structure have been attributed to unique type of GNDs referred to as bundles of concentrated dislocation in gray interiors. This bundle are the results of reaction between the mode 2, traditional mode 2, which is a threading dislocation, and hole patch type dislocations induced by gradient structure. My second topic is just kind of introducing the potential of additive manufacturing, using additive manufacturing to make heterostructural material. Additive manufacturing provides a powerful tool for site-specific designing and fabricating novel HSMs which enhance the mechanical properties. Here we have shown that laminated AM316L stainless steel exhibit extra ultimate tensile strength, extra work hardening due to the effect of interface effective zones. So with that, let me conclude my talk, and thanks to organizer again. Thank the audience for listening to me.
Thanks, Huajian, for the great plenary talk. We have a few minutes for some questions. Huajian, I will ask you the first question. You talked about the BCD. In experiment, we also found a low strain localization. Can you give us your opinion? Could this be related with local strain bands we're observing?
So your question is, we have BCD, but we have enhanced work hardening, right? We have BCDs. I think the BCDs they're not like high angle green boundary, totally kill dislocation motion, right? Usually the problem with the traditional strengthening strategy by refining green boundary, you introduce high angle green boundary, you kill dislocation motion. But BCDs, they're obstacles, they're like more like twin boundary. They're obstacles, but yet they still allow dislocation reaction. Now they have the stair rods, they induce accumulation of dislocation. They make it more and more difficult for dislocation to like obstacle, like a traffic jam, right? But still, you can push them with a higher strength. You can still push them, move them. So this is a little bit of idea like twin boundaries, in that sense, right? So we know that twin boundaries have a very good work hardening properties. So I think the BCDs they're geometric necessary dislocations. They're not green boundary, so right? They are obstacle to dislocation motion. Yet they still react to stress. They can still allow deformation to proceed.
Thank you. Do you have any question from the audience?
Interesting talk, Huajian. When we look at twin boundaries are very special. If you look at other kinds of interfaces and grain boundaries, they can be very different in terms of how they transmit, absorb, block dislocations. So it seems to suggest that there may be opportunities in terms of controlling texture and things like that, that you can control, do the grain boundary engineering. So given that, do you have any idea of what you should be trying to achieve with grain boundary engineering in these kinds of applications of heterostructured materials?
Yeah, Dave, that's a great question. Yeah, that's a great question. So far, we've been observing advantages of twin boundaries. We understand, right? So they're unique advantages in they're different from other grain boundaries, like you said. So grain boundary engineering is very promising, but unfortunately, we do not have a strategy to optimize, right? To see where the maximum is. For example, in this gradient nano twin structure, it's still unknown that what is the optimal, what is the limit? I think this is a little bit unclear. Although my former postdoc, Haofei, he's done a little bit of work on the machine learning, other things, but still the mechanism, how do we achieve or optimize things? How do we do the best? Or where's the limit? These are still open questions. I think it's a great question. So one of the things we say, traditional, we call mechanics of material, right? You give me material, I can characterize, tell you why it behaves so, right? I think in the future we have a so-called mechanical material. Mechanical material is like, how do we design the microstructure to achieve a target property or optimize target property? That one's still something to be worked on. I think all of us can still, lots of research to be done in. I have all this powerful technique to make gradient structures, to make twin boundaries. I can do all these fabrication techniques. Now, can I optimize, start optimize, right? Can we achieve, if I wanted this property or that property or combination of this property, what kind of structure can you tell me? Like an inverse of a mechanics of material approach. I think there's a lot of research opportunities there. Yeah, but thank you for your great question and comments.
Huajian, thanks for your excellent talk. We'd really like to thank Huajian again.